Hi there. So today we're going to talk about section 4.2, which is going to be comparing exponential and linear functions. These are really fun things to do, and primarily what I'm going to do is kind of give you the basic scoop of how to do these, and then I'm going to work through a whole bunch of different examples to reinforce them. Okay, so let us begin. So we are comparing exponential and linear functions. All right, and we're going to look at these in the context of tables, of graphs, of word problems, so it'll be all over the board. So let's consider the following. Suppose we have this big table. So x is 0, 5, 10, 15. And suppose I have a function f of x, and we have 7, 14, 21, 28. And then suppose my g of x is 1,000, oops, and I am going to make one change up here, so hold on a second, 1440 and 1728. I know those seem very random, but actually I'm going to just be nice and make it 0, 1, 2, and 3. Let's start out chill. All right, so essentially what I did is I made one table instead of two separate tables. It's really just a sign of laziness. Okay? Now, what I'm going to do first is look at my function f of x. When we do that, this g of x is totally irrelevant. Okay? And then after we look at our function f of x, we're going to look at our function g of x, in which case we're going to totally ignore our middle row. Okay? So, what I would like to do here is as follows. I want to ask myself, is my function f of x linear, exponential, or neither? So, it's a reasonable question to ask ourselves, given a table, if a function is linear or exponential. If it's neither one, then you just say neither, and you don't need to go any further than that. So, let's first consider f of x. Well, what we need to do is ask ourselves if there is a pattern here. Notice these are increasing by 1, and each of these are increasing by 7. So, f of x. Is there a pattern? And our answer is yes. As our x values change by 1, our function values are increasing by 7. So let's ask ourselves, since it's linear, okay, remember back to our lecture last time, a function is linear if it changes by the same constant amount, okay? So let's ask ourselves then to write the equation of this function. Do I know my y-intercept? I claim I absolutely do. Remember, it's my value of my function when x is 0, so we have that to be 7. And I also claim we know what our slope is. Again, you can actually compute it. It's the change in y values over the change in x values, and we saw that the change in y values was 7. Okay? Now, let's ask ourselves about our function g of x. Let's first ask ourselves if g of x is linear. Okay? If it's going to be linear, then it needs to change by the exact same amount each time. Well, notice as we go from here to here, it changes by 200. But in this next one, it increased by 240. So we don't even have to go one step further. We can see that it does not change by a constant amount. So is it linear? We'll say nope. So now let's ask ourselves if it's exponential. Okay? And this is probably the new part of this section. Now, if it is an exponential function, what does that mean? Well, remember, it changes by the same relative amount each time. So, given a table, the way to check whether or not your function is exponential is you look at the ratios. The ratios need to be constant. Okay, what do I mean by ratios? Well, take each function value divided by its previous function value. Remember, ratios are just fractions. So we need to compute 1200 over 1000. Then we need to compute 1440 over 1200. And then we need to compute 1728 over 1440. Okay? If when we do this division, we get the exact same value, then we say yes, it is exponential. If two of them are the same, but then the other one is different, it is not exponential, okay? So these must be the same. And I claim, in fact, for each of them, they are the same. Okay, we're going to get 1.2. Okay, now, here is the cool thing. Once you have this ratio, you can get your exponential function. Okay? And I'm going to show that to you. This actually gives you your value that goes in parentheses. So if I want to write g of x as an exponential function, remember that's like a times b to the x power? Well, what was our a? A was our initial value. Okay, in other words, our function value when x is 0. And here we have that a is 1000. If we want to know the base of our exponential, once you compute these common ratios, that gives it to you. Okay, now what does this mean? Well, notice since my base of my exponential is greater than 1, we know that it means that it's growing. How much is it growing by? I claim it's growing by 20%. Remember, it's 1 plus the rate. Okay? So, let me just make a couple of generalizations here. And then we are going to practice with a lot of different types of questions. So, given a table, if the change in x is constant, okay, you need to be sure that your x values are also changing by the same amount, and the difference of consecutive y values is constant, then you have a linear function. Okay, and again, given that, you can compute your slope because it's just the change in y values over the change in x values. And even if you're not given your y-intercept, you certainly can find the equation of the line because obviously you're given a certain number of ordered pairs. Okay? Now, on the other hand, given a table, this is why I wrote it long across so I wouldn't have to rewrite too much. If the change in x is constant and the difference between consecutive, or let me say this, if the change in x is constant and the ratios of consecutive y values is the same, then we have an exponential function. Okay? And a cool thing relating to those exponential functions is once you have the ratio, you have the base for your exponential function. Okay, so in that previous example, we got that base of 1.2. That gave us essentially our b value, and we saw that it was growing by 20%. Okay, so what we're going to do now is practice with a lot of different examples. Okay, my hope is that after we go through all of these examples, you kind of get the rhythm of how to go about doing each of these exercises. So let's take our first example. Suppose we have some town and the population is 5,000 at t equals 0. In other words, initially. That's another way I could phrase that. Okay? And we're going to have TB in years, by the way. Okay? Part A. If the population decreases by 100 people per year, we want to find a formula for the population at time t. All right, so the first question we need to ask ourselves is this linear or is this exponential? Notice it's changing by a constant amount, and therefore we know that this is linear. Okay? Now, the amount that it increases or decreases by gives us our slope. The thing is, notice it decreases by 100 people, so that's going to be negative 100t, and my initial population is 5,000. And that's that. Now, on the other hand, if the population decreases by 8% per year, we want to find a formula. Okay? Notice here it's not decreasing by a constant amount, it's decreasing by a essentially relatively constant amount. Another hint, when you're given a general percentage, that's a hint, hint, nudge, nudge, you got an exponential function. So if we want to write the formula, again, you start out with your initial value, which in this case is 5,000. Okay, I know it's raised to the t power. I need to know what goes in parentheses. Well, remember, since it's decreasing, you take 1 minus the rate. So we would take 1 minus 0.08 to get 0.92. And there it is. Alrighty. Let's do another one very similar to this. Now what we're going to do is we're going to say P stands for the price of a gallon of gas in T days if the price is $2.50 on day T equals 0. Okay, so our initial price is $2.50 for a gallon of gas. Let's first do this if the gas prices are increasing by 0.03, in other words, 3 cents per day. Is this linear or is this exponential? I claim since it's a constant amount, it's linear, and that also gives us our slope. Since it's increasing, we put 0.03t, and our initial price was $2.50. All right, what if it was decreasing by, say, 4 cents per day? This is still linear, but what do we know about our slope now? Since it's decreasing, it's a negative slope. All right. What if for part C, I say it's increasing by 2% per day? Is this linear or is it exponential? It's going to be exponential, again, because it's growing by a relative amount. So now we take our initial value, which is $2.50. Since it's increasing, we take 1 plus the decimal amount, so it's times 1.02 to the t. And last but not least, what if we say it's decreasing by, oh, it does not really matter, 4% per day? Can we write this function? And I claim, yes, we absolutely can write this again. It's an exponential function. My initial value has not changed. The only thing that's going to change is what goes into our parentheses. Since it's decreasing, remember you take 1 minus the decimal form. So we're going to get 0.96 to the t. All right. So my main point here was to contrast between when it's verbally given to you, if it's going to be a linear versus an exponential. All right, now we're going to do ones that look a little bit different, but it's okay. I'm going to show you how to do these, okay? Suppose I want us to find, say, g of t equals a times b to the t. In other words, I want to find the equation of my exponential function if I'm given that g of 10 is 50 and g of 30 is 25. Okay? So now what we're given is essentially 2 ordered pairs. I think you'll grant me that one ordered pair is 10, 50, and the other ordered pair is 30, 25. Now, one of the things that I want to point out to you is the following. Notice as your t values or your independent values are getting larger, aren't your function values getting smaller? So in this case, we're going to be looking at something decreasing or decaying, okay? Now, why am I even mentioning that? The reason why I'm mentioning that is that gives me the intuition in the back of my head that this number in parentheses, my base of my exponential function, is going to be between 0 and 1, okay? Now, the other thing that I want to point out about this problem is it's kind of a bummer because we're not even given our initial value, are we? Okay, we would know that we were given the value of a if we had 0, some number. Okay, so we don't have a, we don't have b. Yeah, this is kind of an uncomfortable situation. So let me show you how we would go about computing this. Okay, what I would do is look at the ratios of each of these ordered pairs plugged into our function. In other words, will you grant me that I can say that, say, 25 is equal to a times b to the 30th power? Okay, right? This is my independent variable. So when b is equal to 30, my function is equal to 25. What else do I know? I know that when b is equal to 10, my function is equal to 50. Could I have written them the other way? Yes, I could have, okay? Either way you write these is fine. You're going to get to the same place. Now notice, I'm looking at these ratios, okay? So on my left side, I've got 1/2, right? 25 over 50 is 1/2. Well, a divided by a, those go away, and now we're going to use our properties of exponents. This is why they're really crucial. B to the 30th over B to the 10th. Remember, when you divide two things with the same base, you subtract your exponents. So I claim we're going to get b to the 20th. All right, now, we don't want b to the 20th. We want to know what b is. How are we going to get to b? Well, how do you undo raising something to the 20th power? You essentially take the 20th root. In other words, what I'm going to do is raise both sides to the 1 over 20 power. Okay, why? Because remember, when you raise something to a power, raised to another power, you multiply your exponents. And 20 times his reciprocal, 1 over 20, is just 1. This is going to give us our value of b. Now, this is where a calculator is really handy. Essentially, let me show you what I'm going to plug into my calculator. I'm going to plug in 0.5, and then I'm going to use my caret to say I'm raising it to a power, and then in parentheses, I'm going to put 1 divided by 20. Okay? You could put 1/2 here. Just make sure you put 1 divided by 2 in parentheses so that you know, or so that your calculator knows that it's raising the whole thing to this power. So 0.5 raised to the 1 over 20th power is about, I'm going to round to 2 decimal places, 0.97. So, do you agree that this far, what I can say about my function g of t is it's equal to a times 0.97 to the t power? Notice my base is between 0 and 1, just as I predicted, given the fact that this is decreasing. Okay? I'm not done. I now need to find my value of a. How do I go about doing that? I plug in either one of those ordered pairs. Okay? I'm looking at 1050 first, so I'm just going to plug that in. I know that my function is 50 when my t value is 10. So I'm going to use my handy dandy calculator and compute 0.97 to the 10th power, and you're going to get some nasty decimal. But essentially, the way to solve this, in other words, to get the value of a, is you're going to take both sides and divide it by this value. Okay? So what I would type into my calculator is 50 divided by 0.97 raised to the 10th power. And you get a to be about 67.8. So therefore, my function is 67.8 times 0.97 to the t power. I know that's a lot of work. Don't worry. I'm about to go through a few more of these. Okay? But in general, when you want to find the equation of an exponential function and you're given 2 ordered pairs, this is a really nifty way to do it. Okay? So, let's do the same sort of thing, but let's take different values here. Okay, now we want to find our formula for f of x. It says, hey, it's an exponential function such that f of negative 8 is 200 and f of 30 is 580. Okay, I'm going to go through the exact same thing that we just did. I'm going to write these guys as ratios. Okay, notice we're not given our initial value a, nor are we given the base of our exponent. Okay, so I was just told to change the marker. Here we go. Let's use this guy. Well, again, I'm going to write these as ratios. Okay, I know that a times b to the 30th is 580. I know that a times b to the negative 8th power is 200. Okay, one thing I'm going to point out, notice as my x values are getting larger, so is my function. Therefore, I can expect the base of my exponential to be greater than 1, right? Because it's growing. Well, again, our a's cancel. We have 580 divided by 200, and that gives us 2.9. Check this out. I'm dividing two things with the same base, so I subtract the exponents. 30 minus a negative 8 is 38. All right, I don't care what b to the 38th power is. I want b. So I'm going to raise both sides to the 1 over 38th power. So I'm going to compute 2.9. And again, I'm going to raise that to the 1 divided by 38th power. And when you do that, you should get about 1.03. So far we have f of x is a times 1.03 to the power of x. All right, now what I'm going to do is take one of these ordered pairs, plug it in to get my value of a. I'm going to take this bottom guy and say, well, 580 is a times 1.03 to the 30th power. To get a alone, we'll divide both sides by whatever number 1.03 to the 30th power is. And let's compute that. 580 divided by 1.03 to the 30th. And we get 238.95. So 238.95 times 1.03 to the power of x. And that's our final answer. I never said it would be pretty. All right. So don't worry, we're going to be doing more of these. It's just going to, instead of being written out in a sentence, what I'm going to do is take a graph. Okay, let's do this guy. And we will be talking about the graphs of exponential functions in the next section. But let me say that that's 50, and this happens to be the ordered pair 5, 20. All right. One thing first, whenever you're given your y-intercept, you want to be at least have a smile on your face because that gives you your initial value. So already, if I'm going to write this as a times b to the power of x, I know what my a is. I know that I'm looking at a being 50. Okay? So celebrate those situations. Well, again, when we want to find the equation of an exponential function, we're looking for two things, a and b. We have one of them already, so now we just need to find b. Well, we've already used this point. Let's plug this point in. We know our function is 20 when our x value is 5. Can I solve for b now? I claim I can. The first thing we want to do is isolate our exponential guy. So what I'm going to do is divide both sides by 50, and I'm going to get 2/5, or you can write that as 0.4 equals b to the 5th. Now again, I don't want b to the 5th, I want b. So what I'm going to do is take both sides and raise them to the 1/5 power. And if you do that, I'm just going to go to 2 decimal places, you get about 0.83. So therefore, I claim my function is 50 times 0.83 to the power of x. Now I want to pause for a second and say that notice my function is decreasing, so it makes sense that the base is less than 1. Okay? All right, so the moral of that story is when you're given your initial value or your y-intercept, it sure makes life a lot easier, okay? So let me take an example with a graph where we're not so lucky. How about this guy? So suppose this is our graph, and I've got the ordered pair 40, 80, and then I have the ordered pair 120, 20. All right, total bummer, we're not given our y-intercept because that would already give us one of the values, okay? This brings us back to the same type of scenario that we were just working on, okay? I can take each of these ordered pairs, plug them into my exponential function, and write them as a ratio to compute the values. For example, I could take this guy first. I could say that 80 is equal to a times b to the 40th. And 120 is a times b to the 20th power. Okay? So at this point, well, the a's cancel. Over here, we can reduce that down. This reduces down to 2/3. You could write it as 80 over 120. You don't even have to reduce it if you don't want to. And b to the 40th divided by b to the 20th is b to the 20th. Remember, when you divide two things with the same base, you subtract your exponents. Well, in order to get b, I raise both sides to the 1 over 20th power. And if you compute that, you're going to get b to be about 0.98. So at this point, I have a times 0.98 to the power of x. Do you see how even though initially we were given a graph, it still flows the same way? Okay, that's real important. Now, to find our value of a, again, you're going to take either one of these ordered pairs and plug them in. I know that when x is equal to 40, my function value is equal to 80. So to find our value of a, we would divide both sides by that. So I would plug in 80 divided by 0.98 to the 40th power. And we're going to get about 179.5. So my function is 179.5 times 0.98 to the power of x. And if you're rounding to a different number of decimal places than I am, don't worry. Your homework will always specify how many decimal places to round to, and I will do the same on any test or quiz. Well, yes. All right, let's do a couple more, okay? We're going to do one more involving a graph and then one more involving a word problem. Okay, so we want to find the formulas for the following exponential functions. So this is P, and then pretend that's not a line. Let this one be Q. And let me just mention that this ordered pair is 1040, and this ordered pair down here, pretend this is a decent graph, I'll just thicken the curve, is 1520. So notice I have two different exponential functions. Let me rewrite this so that you can see it clearly. And I want to find the equations of both of them. Notice my function p is increasing. So in the back of my head, I am thinking to myself that the base is going to be greater than 1. In a similar manner, notice q is decreasing. So in the back of my head, I'm thinking that my base is going to be between 0 and 1. Now, I'm going to do p first. The reason why is I claim it's an easier guy to deal with. Okay? So we'll call him p of x is a times b to the x. Why do I make the claim that he's a bit easier to deal with? Because we're given our initial value. We're given our y-intercept. So already I know that my function p is 20 times b to the power of x. Okay? Can I find my value of b? Absolutely. I have another ordered pair. I'm going to plug them in. I know that when x is equal to 10, my function is equal to 40. Okay, so how do we go about solving this? The first thing we do is we isolate our exponential. We divide both sides by the number in front. So I get 2 is b to the 10th power. And then in order to get b all by his lonesome, I raise both sides to the 1/10th power. And if you compute that, you're going to get 1.07. So I can conclude that p to the x is 20 times 1.07 to the power of x. Notice the base of my exponential is greater than 1, which completely jives with the fact that it's increasing. Okay, now let's do q. Okay, again, I know that q of x is of the form a times b to the x. Unfortunately, this is going to involve a little bit more work. Okay, again, what do you do when you're given two ordered pairs? You form the ratio of them. Okay, I can say, for example, doesn't matter which one you put on top, that say 20 is equal to a times b to the 15th, and 40 is equal to a times b to the 10th. Okay, 20 over 40 is 1/2. My a's cancel, and b to the 15th over b to the 10th is b to the 5th. So to get my value of b, I take the 5th root of both sides. So I take 1/2 raised to the 1/5 power, and I'm going to get 0.87. So at this point, I know that q of x is a times 0.87 to the power of x. Okay, so we have at this point q of x is a times 0.87 to the power of x. And now what we need to do is find our value of a. So what we can do is take either one of these ordered pairs and plug them in. We know that if we plug in x equals 10, that my function is equal to 40. Okay, so in order to find our value of a, what we're going to do is divide both sides by 0.87 to the 10th power. If I do that, I get a to be approximately 161. So notice my function here is 161 times 0.87 to the power of x. Now again, I want to make just one quick comment pertaining to my answer here. Okay, notice that my initial value is really big, and notice that this is not going to be crossing my y-axis for a little while. So my a value makes entire sense, and again my b value also makes entire sense because my b value is between 0 and 1, and this function is decreasing. So that completes this section. Thanks.